The digital world is associated, so to speak, with a particular vision that is linked in a way to science fiction. Yet, although this is warranted from a cultural and historic point of view, it is worth stating that the reality is far removed from this vision, and that we are actually living in a digital space which completely shapes our everyday lives. We use digital technologies and devices to communicate with each other, to obtain information, to live, work, and be together. The digital world is our coexistence, aided by computers, along with information and communication technologies. It is certainly not a paradise made up of bytes, a dream world, a fantasy in which we live disembodied and without physical substance. Every time that someone talks about a digital future, they talk in a way that is either extremely enthusiastic or that is extremely concerned. First of all, enthusiastically, meaning that there will be a whole range of new possibilities for change, including, for example, being able to produce, manufacture in a different way, work in a different way, have a more vibrant social life, etc. And then, correspondingly, a whole range of serious concerns relating to destruction of the social fabric, people withdrawing into themselves and a loss of human contact. Both of these attitudes are equally correct. After all, people have been taught that digital technology only means practices, knowing how to make use of existing things, knowing how to use a computer, the internet and all of that. And that, I believe, is an extremely dangerous attitude. We need to do it a little, but not too much. The fact that we are able to intellectually grasp how an object associated with our digital practices works allows us to take control of this object and not to submit it to its design, customs, or even its introduction more generally, in the workplace or at home. At school, everyone has heard of mathematics, physics and chemistry, and in terms of computing, children and young school pupils, and subsequently high school students, are at best taught to use tools, frequently office tools and now internet tools, but hardly ever to really explore these sciences and to apply and understand them. Computational sciences is an enormous field that will cover all sciences that are based, from the outset, on the digitization of information of absolutely any kind, including images, measurements, sounds, text, etc. Historically, the two oldest are computing, which relates to ways of processing digital information, followed by applied mathematics, which itself relates to mathematical algorithms that will enable the world to be shaped, monitored, simulated, etc.
Cryptography is a science that is as old as writing and is truly a science that stands midway between computing and mathematics. Cryptography makes use of relatively complex mathematics, which may involve number theory tools, discrete mathematic tools, and probability tools. And these mathematical techniques are not always very easy to access.
Little by little, other sciences are being compelled, and happy, to become highly digital. Doubtless this began with astronomy and, naturally, continued with physics, which is increasingly simulating its experiments, in addition to conducting them. It's quite clear that there are a great number of experiments that cannot be conducted in astronomy and physics, such as exploding a star, for example. This cannot be done in a laboratory. It's pretty rare and can only be observed from a great distance. However, extremely precise simulations can be carried out. Of course, there is climatology, which is attempting to understand the climate, and as there is only one possible experiment, trials cannot really be carried out. Bioinformatics has become an extremely important area around the world and has truly enormous potential. Medicine too has become entirely computerized and digital. Modeling the heart and other organs is extremely important in understanding how they work and in understanding diseases and preparing for surgical operations, for example. There are many other sciences, with botany now studying plant growth, how buds produce leaves, etc. In other fields, such as social sciences and humanities, for example, or archaeology with digital facets, or linguistics with digital facets, in short, a very large number of sciences have now adopted this digital approach. Computational science researchers have produced a certain quantity of results, progress and tools, and therefore, quite simply, machines, languages, compilers, and software used by other scientists. Therefore, the main reason is genuinely the results of progress in computational sciences, which have moved into other sciences. The second reason is obviously that companies have marketed a certain number of these innovations, which have not remained solely within computational science research laboratories, but which have been allowed to pervade society pretty well everywhere, and to enter laboratories used by other sciences. What's interesting is that, in other respects, these other sciences occasionally throw up new issues and new research topics, and it's therefore ultimately this to and fro that is extremely productive and that enables all aspects of science in general to advance. Computational sciences face genuinely scientific challenges, beyond societal and democratic challenges, or the issue of responsibility that may be talked about. Whether this is a question of machines, and therefore new architectures or new networks with their ever-increasing reliability and speed, this is clearly an initial challenge. We're currently dealing with the construction and consolidation of increasingly complex systems, beginning with IT system interactions, the cloud, etc. A second, very important challenge, which is being widely discussed at the moment, including by the general public, relates to data. Today we're producing far more data than in previous centuries. How to retrieve information from this data is a genuinely significant problem. How to give this data credibility? What kind of certification should there be, including within a business professional cloud? These are the kinds of questions that arise. More and more will be demanded from data production and interconnection methods, from semantisation, from the control of personal data, etc. This means that requests addressed to scientists in these particular fields will not decrease, but simply that they will be simultaneously asked to go further in terms of complexity and also to be more accessible.
The fact that today a lot of data is processed directly and digitally and is dematerialized is tremendous, because this allows for very easy access, straightforward reproduction of data and large-scale data storage. But it is also, and this is the obvious downside, relatively dangerous, because this means that there is a quantity of data that is exposed. Therefore, there is clearly a need to secure this data in order to attempt to slightly reduce this vulnerability, or at any rate to restrict it as far as possible.
Third sizable set of issues is the problem of models. How are we going to structure all this information? How are we going to model a certain number of issues in order to attempt to resolve them? When it becomes a matter of understanding changes in agriculture, transport and the road network, or changes in our travel, we currently make use of models. We call on people involved in computational sciences for aspects that do not lie within the digital world, in the sense of the world of internet users or mobile users, for example, but activities that are quite commonplace and ordinary. A fourth aspect that is really important, which comes back to a degree to uses, and which relates to users, is that it's possible to develop an excellent piece of software, but if the end user cannot find what he or she is looking for in it, this software will not be used. So how is it possible to ensure that the issue of the interface between the user and these digital systems is genuinely accepted? This means that computational sciences will also need to be sciences that incorporate these interactions, not as it used to be, in a world where people would adapt to machine and where machines would be at the heart of mediation between humans, but in a more comprehensive and sophisticated way, involving our everyday environments, with abundant interactions between people, robots, sensors, etc. Scientists produce new knowledge that, in a certain number of cases, turns into innovations, and among these innovations, some may result in progress. Therefore, one of the issues that arises is knowing how to transform these positive results of research into progress for our society.
Fortunately, we're starting to see computing as sufficiently important to be taught at secondary school, or even earlier. And now for everyone to receive training in computing is key, like learning to read, write, count, and handle a certain amount of knowledge. Computing must form part of everyone's basic knowledge, and this is something that is important.
Thinking about the future means standing in a world where, in a few years, things will probably be quite different in terms of natural resources and demography. And therefore, we will need to anticipate these changes in society and in the work of computational researchers, who must be able to succeed in doing their best, and not just doing more, in generating greater adoption, and not more enduring, and arriving at a situation where computing encourages living together.